methods. I've been forgetting. All right, so direct method, we've only been doing the direct method so far, but what happens if you have an if and only if statement? Now, first of all, remember what an if and only if statement is. It means you really have two statements. You have if P then Q, but you also have if Q then P combined in there, okay? So the first thing that you would do, just like with an if P then Q statement, is you want to identify what those two simple statements were out of your if and only if statement. Okay? Now the second thing that you do is the method. First thing is you prove your if P then Q. Don't overthink it. Then you prove if Q then P. So these guys do have a tendency to have twice the work because it's really two questions in one, if you will. And this is something we talked about before. Logically, this means whenever you have whatever the P statement is, you automatically are going to have whatever that Q statement is. And I'll go ahead and, since there was space in the slide, I also wrote down how to deal with a counter example as well. So the other type of thing that we wanted to deal with at the, hopefully the tail end of today, but it might actually be at the very beginning of next time, is how to deal with a counter example. A counter example is you have some statement. Maybe it's an if P then Q statement. Maybe it's an if and only if statement. But you've got some sort of statement that you want to figure out if it's true or false. And here is, you're going to look at some examples. Now, if you're proving something, examples are awesome because they show you that, hey, yeah, it looks like it works. Like several of you guys were showing me where you wrote out a bunch of examples of perfect squares and you physically calculated their differences, and yeah, they were all odd. Those would be examples. They do not prove that something works, but they definitely give you an idea of, hey, I feel like this definitely should work. Now, a counterexample is where you think maybe the statement isn't true, and you find an example where the statement actually isn't true. And remember, this here, in terms of us proving, if we were in truth tables, we'd be looking for tautologies, where something is always true. So as soon as you find an example where the statement isn't true, that means you don't have a tautology. It's not, your statement you're trying to prove isn't always true, so that means it's not a true statement. In other words, result, this disproves your statement until you actually X the statement if you still needed that fact. Okay. All right, and we already talked about that actually. So let us look at an example of an if and only if statement, and then near the tail end of today or the beginning of next time, we'll look at counterexamples. So this is an example of an if and only if statement. I believe this is actually the example that we had yesterday of what an if and only if statement looked like. Or maybe it was Friday. I can't remember now when we talked about it. So we want to prove that if n is odd, or actually, let me read what's written. Prove that n is odd if and only if n squared is odd. Now, this is broken up into two components. You're looking at when n is odd, and you're looking at when its corresponding perfect square, n squared, is odd. Okay? So if we look at these guys, maybe we take this first part here to be p. Maybe we take the second part here to be q. So what we would like to do is we need to, since it's an if and only if statement, prove if p then q, and also the reverse, or the converse as it's officially called. So for this slide here, I'm going to do the forward way, so if p then q. And we're going to go ahead and use the direct method. Why? Because it's easy and straightforward. So in terms of notation, I went ahead and put a little, inside of parentheses, the arrow. This here is in no way, shape, or form something that's required for your proof, and in fact, most people really hate to see it there. But it's scratch work that reminds you which direction you're going. This tells you start with n is odd, and conclusion needs to be n squared is also odd. So we'll start off and we'll say, and I'll go ahead and put the labels here on the side as we go down. So we'll start off and say, we've got already the symbols n. So if n is odd, that means it's got to be an integer. So let n be an integer, and we'll go ahead and assume that n is not negative, but this actually totally works if n is negative too. Okay? So we actually didn't need that. Now, suppose n is actually odd. Okay? So that part can work for either of the two directions, but now we're actually in this forwards direction. Suppose n is odd. Now, using the definition of odd, we can rewrite n as 2 times k plus 1, where k is some integer. We don't know which one, but there's some integer that makes this work. Okay? Now, any guesses what we should do on the next line? Don't overthink it. Anybody have a guess of what we should do next? So far, we've just been telling our reader, or our future selves, depending on who's actually going to read this, that we've told them, hey, n is an integer, n is odd. If n's odd, here's how we rewrite it. So we're really just talking about this setup of n being odd. But we want to get to n squared is odd, so somehow we actually have to get to n squared. So what should we do to figure out if n squared is odd? Anybody have a guess? Don't overthink this. If you're still thinking about it and not sure, you're probably overthinking it. So gut response, what do you think we should do? And yes, I'm totally waiting on you guys to send in answers. Ooh, lots of guesses. None of them are awesome yet. There's a super, super helpful guess, and it comes from the work that's above the then. Any guesses what it might be? What do you know for sure right now? Or what have we established already so far? See if that helps with the guess. Just plug in. So there were several guesses. One of them was just plug in. So just plug in. That's all you got to worry about right now. Okay. Now, that being said, we want to get over here and show that n squared is odd. Okay. Well, if n squared is odd, that means we have to have n squared is 2 times something that we don't know what it is plus 1. Okay? That's using our definition of odd. And if you wanted to, you totally could put in the last sentences right here. They're not going to fly in for me because that's not how I did the timing. But your last sentence down here could actually be n is odd, second to last sentence, using our definition where once we have established this. So somehow we need to rewrite this expression that we currently have, the 2k plus 1 whole quantity squared, as 2 times something plus 1. Don't overthink this. Any guesses what the next line should be? Again, don't overthink it. If you're thinking about it for more than about 5 seconds, you're probably overthinking it. Gut response. What should we do if you're given this? Yeah, so there's a guess that came in that was totally right. Just multiply it out. Okay? So now we've just multiplied this out. We squared the 2k, so that gives us 4k squared. We multiplied the inside, the outside together if you FOIL it out. So that would be 2k, not 2k, 4k. And then when you square the 1, you'll get the 1 over here. Now, is that something that we could rewrite in the form of 2 times something plus 1? Well, we definitely have the plus 1. Could we rewrite the 4k squared plus 4k as 2 times something? In other words, can we write the stuff that I'm about to underline as 2 times something? Can you factor a 2 out of those first 2 terms? Remember, this guy that started up here at the top, that's the format we're trying to get to. Yeah, so you go ahead, you factor out a 2, and what will happen? My cursor went away. We'll have 2 times, well, in the first one we'll pull out a 2 and we'll get 2k squared. In the second one we pull out a 2 and we get 2k. So that means now we have 2 times something plus 1. Now, the only thing you have to confirm is this something that you were trying to get for your n squared, which we totally have right now, has to be an integer. So we go back to what k was. So k here was an integer. Now, if k was an integer, is this expression inside of the parentheses still going to be an integer? In other words, 2 times some integer squared plus 2 times that same integer. Is the stuff inside the parentheses an integer? What do you guys think? And the only answers are yes or no. So you got a 50-50 chance. Yeah, so this guy does turn out to be an integer. So since since k was an integer, you are going to get that sort of mess is also an integer. And since this stuff inside the parentheses was an integer, the definition of an odd integer, this tells you that n squared is going to be odd. Okay? And that's it. Okay? Now, when I say that's it for that direction. So that's half of proving the original statement up there at the top. But for this direction, are you guys comfortable with what we did? All right, I'm getting a couple affirmatives, so let us move on to the other direction. So the other direction is, instead of starting at n is odd, we're going to start with n squared is odd. Okay? So same initial statement, same n is odd, n squared is odd, but now we're going in the opposite direction. Now, here's an issue that we're about to run into. When we start dealing with this guy, you start dealing with n squared. In order to transform from n squared back to n, and let me do a little scratch work, which we'll erase here in just a second. So here would be scratch work. You'll have n squared. You say, hey, n squared is that guy. Maybe you actually go ahead and remind yourself that k is an integer. Maybe you don't. Then you start looking at n. You say, all right, well, if I do the same thing that I did before, I plug in, and this would be n is the same as square root of n squared, which would be the same as the square root of 2k plus 1. I needed this guy to be odd, so I have to figure out what goes inside of those parentheses, and anybody spot the snarly horribleness that's about to happen. I'll label this scratch work. Why would I say there's a problem with this? Logically, it is exactly identical to what we just did in the other direction. But what's the problem that occurs? Anybody spot it? No problem with this first line. That's just the definition of odd. The second line, that's totally correct, right? N is the square root of n squared. Well, it's theoretically the positive root. There you go. Right here, when we start plugging in, we get the square root of 2k plus 1. That doesn't simplify into anything nice where we can actually use it over here, or at least not well, at least not without doing something like power series mess. And we're not even going to go there, okay? So this here, when you start dealing with square roots can be nasty to deal with when you start trying to plug in and manipulate stuff because they just don't work as nicely as if you're taking, say, an exponent of 3. Okay? They just don't work that way. So instead of looking at this as a direct method proof, instead we're going to look at this as a contrapositive or a proof by contrapositive. So to remind ourselves, if you originally have, and in our case, we originally have Q implies P here, the contrapositive, or what we're going to do is the proof by contrapositive, that was trying to be a V, is where you flip-flop the order and you negate both of them. So when you negate both of them, we'll get not P, we'll get not Q, and when you flip the arrow, you'll get not P implies not Q. Now, why would we decide to use the contrapositive version of this statement? We want to use the contrapositive version of this statement because if we try to use a direct method, you have this issue with the square root. So if you get stuck, you don't have an easy way or even perhaps any way that you can think of to get out of some snarly situation, this is where you go back and you start over and say, maybe I should have really used the contrapositive of the statement. Okay? So that would be why or when you would use a contrapositive. For our class, it'll come up every so often. This case is a beautiful example of when you'd want to take the contrapositive of the statement. So I'm going to go ahead and erase all the scratch work. Did you guys get everything that you wanted to before I erase the scratch work? All right, seeing nobody yell no immediately, I'm going to go ahead and erase all of that scratch work. And now let's go ahead and look at our contrapositive. Okay. So in terms of the proof, went ahead and did the same initial setup we did before. And in fact, if this was written all on one piece of paper, you'd only need to write this part once where you say let n be an integer. And technically speaking here, you don't actually need n to be non-negative. Okay? Now, let's go ahead and look at our contrapositive. When we look at our contrapositive, notice we're negating p first. So I'm going to claim that we start off and suppose that n is even. Is n being even the negation of p? What do you guys think? Does that look like not p? So statement P was n is odd. So the negation of statement P is N is even. Okay? Now, to do that same thing with Q, anybody have a guess on the negation of Q? It'll be something about N squared. So regular Q says N squared is odd. So not Q would be N squared is. Guesses? We need this because we'd need to know what our conclusion is. And yes, the negation of odd is going to be even. And why is that? Because all numbers are either even or odd. Now, once you start off with N is even, we haven't dealt with even too much today. Most of the stuff we've dealt with today is odd. But remember, the definition of even is just N is going to be 2 times something, where we've called our something K. That's some integer. Now, once we've got that, we're looking for the negation of Q. Well, not Q is N is even, so we're going to be looking at, N squared is even. So we're going to be looking at N squared here. Now, any guesses how we should manipulate N squared? Now, remember what our goal is. Let me put that goal over here to the side. If our goal is to get that N squared is even, we need N squared to be 2 times something. So what do you guys think? What can we do to rewrite N squared using only the information that we've written down so far? Don't overthink this. Well, it turns out once you look at the contrapositive, you can totally mimic what we did previously. So what did we do previously? We had N was odd. We had a formula, an expression for N being odd. We plugged it in. We can do the exact same thing here. Plug in that expression of 2K. Now, we're not at the goal. We're not at 2 times something yet, but could we actually manipulate this? Of course. First, multiply it out and get 4K squared. Then factor out the 2 to get 2 times 2K squared. Now, the only thing left to do is whatever's inside of these parentheses has to be an integer. So what do you guys think? Is 2K squared an integer? Don't overthink it. You've only got 2 answers, yes or no. Is 2 times K squared an integer? Yeah, it is. So since 2 times K squared is an integer, that means N is 2 times some integer, which means by definition it's even. Now we just got to write all that down. So, hey, since K is an integer, the 2K squared is an integer. And then N squared is going to be even by definition. Now, here's the conclusion, and this is the part that I forgot to type up in the slide. When you do a proof by contrapositive, so you're using not the original statement, but the contrapositive of the original statement, you do have to do a final sentence, and this is the sentence I forgot to type in. So what you say is or thus maybe. Should probably restart that a little bit. Eraser. Get back to a pen. Actually, since I can change it, let's go ahead and make that black. So hence, if we're going the direction of if N squared is odd, then N is also odd. Notice I rewrote it in the original wording here by a proof by contrapositive. I can't write a P today. Contrapositive. So you always have that last little sentence that tells your reader what you actually did when it's not the direct proof when you're doing this contrapositive. That way you can get the conclusion as stated. Okay? Actually, it's the full statement, the if-then part of the statement. All right, so that would be what you would do dealing with a proof by contrapositive. Notice when you're actually grubbing around in here, it's exactly the same as a direct proof. The only difference is instead of proving the statement as given, you're proving the contrapositive of the statement. And you only do that if you can't do the direct method normally, or if it looks like it'll be way easier. Okay. So let us look at, actually, let me skip the next example. I'll go ahead and post this next example for you guys. It deals with sets, but let us jump into the example after that, just so that we get to one of these last examples today. And we can go back to the set example if we want to, or I'll just let you guys read it. Okay? So suppose you have the following. Now this one is a little bit different than what we've done in the past. This one actually has an inequality that it asks you to prove, or ask, is this inequality always true? So this example says, prove that 1 plus 2 to the n is always larger than or equal to 3 to the n for any positive integer that you want to pick. Okay? So we're not going to look at fractional integers. We're not going to look at negative integers that really turn the 2 and the 3 into fractions. We're only looking at proper exponents as you think of them in terms of powers, I guess I could say. All right, so what do you guys think? What should we do with this one? Anybody have a guess? Don't worry, I am willing to wait for your guesses. The first thing we should always do, that we've been forgetting a little bit in some of our other examples, is you should always check to see if you actually believe the statement. So what do you guys think? Does that seem like it's a believable statement? Okay, so I've got one vote that you think this is not a believable statement. So let's check it out. So if you actually picked n equals 1, which is the smallest positive integer, you plug it into the formula. On that left-hand side, you'll get 1 plus 2 to the first power, or 1 plus 2. And then on the right-hand side, you get 3 raised to the first power, which is 3. Does the inequality hold when n equals 1? What do you guys think? Is that inequality true when n equals 1? Don't overthink it. Okay, so I got a couple answers. Yes, this inequality is actually true when n equals 1. And let me actually go back and change that color just because it's not going to show up well with all of the typed words. I'm not liking the red, so we'll go to blue. So this does work for n equals 1. But the statement says it actually has to work for all positive integers. So we still need to look at, well, some of the other ones. So maybe you pick n equals 2, which flew in a little bit faster than I meant to. But if you look at n equals 2, any guesses why there's a slash here? So in terms of the actual formula, I just plugged in 2 for n. So we've got 1 plus 2 squared on that left side. On the right side, we've got 3 squared. So what's going on there? What does that slash mean with the inequality? Don't worry, I don't mind waiting. But don't overthink it either. If it helps, think about what the two sides mean. So on that right-hand side, we have 1 plus 2 squared. What does 1 plus 2 squared equal? Or do the easy side, the 3 squared? Yep, it equals 5. So do a quick double check. Is 5 greater than or equal to 9? Yeah, no would be the key answer. So that slash just means, nope, the inequality is not true. Well, according to this statement, it was supposed to be true for all integers, but what did we just find? We found a positive integer where that inequality was not true. So this actually tells you that you have a counterexample. The counterexample is where the statement claims it's still true, but in fact, it didn't work out. And in fact, if you pick any integer bigger than 2, it's also not going to work out because this statement really, this statement right here, the inequality really should have been flipped. So finding counterexamples sometimes is like finding typos. Okay? So when you actually want to give a conclusion, what you would say to this guy is you'd say false. There's a counterexample when n equals 2, and then you'd write out what that counterexample is. You don't. So this part here is like scratch work. Apparently I can't write work. This guy here is like the answer. And then here is where you would go ahead and put that stuff. Now, if you already have the scratch work, it's perfectly fine to type it up just like I did right here or write it out just like what I did here. But if you don't write out your scratch work, you want to still make sure you give the actual example where something failed. Okay? So for those of you who don't like giving scratch work, make sure you still write out that part. Okay? Now, what about this next example? Since that was such a short example, I went ahead and put this next one on the same screen. So here, this next example says, let A and B be integers, where A divides B, so A is a factor of B. Then prove that A always has to be less than or equal to B. What do you guys think? Is this a true statement? Does that seem believable? What does this basically say? It basically says factors are smaller than the numbers they're factors of. So what do you guys think? Does that seem believable? If it is, we'll try to prove it. If it's not, we need to find a counterexample or a place where it fails. So sometimes when you're trying to figure out if you believe a statement or not, you do examples, okay? Especially on things that seem like they might actually work out. So let us pick a pair, okay? So here is, I'm going to call them test cases, simply because we already have the label of example in front of that sentence, okay? And we'll do a couple different ones and see if it works in which of these cases, all right? So you want to, when you pick your test cases, when you pick your potential counter examples or your ones where it'll work so that you believe this in prep for your proof, you want to make sure that all the conditions are there. So the if part of this statement would include your two symbols, A and B, and it would also include A divides B or A is a factor of B. So you have to make sure you pick an A and a B where A is a factor of B. So maybe you pick something like A equals 2. So then you would have B equals, I don't know, maybe 6. Okay? So in this case here, notice 2 is a factor of 6. Double check. 2 is a factor of 6, right? I didn't screw that up yet. Hopefully you're all thinking yes. Why? This is because 6 equals 2 times what? What should I write after that multiplication symbol? Hopefully you're all thinking 3. So then do a quick double check. Is the inequality true? So for the guess that we just picked, so for the test case we just picked, where A is 2 and B is 6, did we actually get that A is smaller than B? Does it work for this little baby example? All right, I want one answer, vote for yes. What about the rest of you? Do you guys think that the inequality works in this situation? Yeah, it seems pretty reasonable, right? All right, I got a couple more votes for yes, so yeah, this one works. Now, we would like to try to break this thing, okay? So if we want to try to break it, anybody have a guess on how we could? Well, the only way to break it is you still have to pick an A and a B, where A is a factor of B, but you need this inequality to flip. Well, it turns out this statement works if A and B were both positive integers. So pick any pair where the two numbers are both positive integers, and this is going to work just fine. It's one of the reasons it seems very believable, because as long as you're dealing with positive integers, it's going to work. Ooh, and I have a guess. Yeah. So the guess here is A equals -5 and B equals 10. Make sure I wrote it down. So let's check it out. So in this particular case, yep, -5 is a factor of 10. That's because 10 equals, was that -2 times negative 10, and technically there should be parentheses around those guys with negatives. And so when we look at this, we then need to look at the comparison. Do we actually still get the inequality where the A is less than B? And it looks like negative 5 is still less than 10, but that gives us an idea. Anybody have an idea of what idea that last example would give us? I'm going to claim we could still do a 5 and a 10 here. Yeah, flip the negative, and it'll actually give you a counterexample. So let's see why. So here, we'll still have that 5 divides negative 10, or is a factor of negative 10, because negative 10 is negative 2 times positive 5. But when you start looking at is 5 less than or equal to negative 10, right here, that answer is a big fat no. Negative 10 is the smaller one. It does turn out that if negative numbers are in play, sometimes the inequality works, and sometimes the inequality doesn't work. Now, all of this stuff with the test cases, that's your scratch work. So here would be your actual conclusion. You would say, hey, nope, this statement is false. Okay? Pick A equals 5, B equals negative 10. Then what do we get? We do get that 5 is a factor of 10, but 5 is larger than negative 10, which is exactly the opposite result of what we were supposed to get. Okay, so that guy would be a counterexample, but notice we had several test cases, several examples that we tested out or that we looked at before we got to one that actually was a proper counterexample. So one of the first things that you do when you look at a proof, and this is even if you decide you're actually going to prove it, you believe it, is look at a couple of examples. See if you get to the point where you actually believe this statement. If you get to the point where you're going to believe the statement, you have to do a proof. The examples do not, if you have all examples that work, that doesn't prove anything because there are infinitely many potential examples and you can't check them all. Okay? If, however, you get an example that doesn't work, that's a counterexample. Stop there and you just write it up and say, hey, this is an example that makes this statement false. Okay? But that would be the crash course in dealing with counterexamples. I've got, actually, that takes care of everything with counterexamples that we were really planning on talking to. So that takes care of everything in sections 5 and 6. We'll look at mathematical induction next time then. And since induction has a tendency to be tied closely with examples with sequences, we'll probably look at a little bit of properties of sequences tomorrow as well. Okay? So I'll stick around if there's any questions, but that is everything that I've got planned for today.